Good afternoon. It's Ken Askew, Director of Sales at TechXtend. I want to welcome you to today's webinar, Explaining Parallelism Using Intel Compilers. Brief agenda first, a bit about TechXtend, and then today's webinar hosted by J.D. Patel, compiler TCE with Intel, followed by question and answers period, and then a summary. Evaluated reseller and developer and infrastructure tools. We can be found on the web at www.techextend.com, and the Intel products fall under our ALM Worldview ecosystem. We are Intel elite Intel partner in North America. Normally, Program Paradise has a 3-year period of being the source for developer and database tools. We all focus on virtualization and cloud computing, storage data management, business intelligence and information management, and device management. Under LM Worldview software ecosystem, we provide industry-leading tools for your end-to-end development needs, including defining, designing, developing, testing, deploying, and managing. Things over to Jay to start today's presentation. Jay?
Thank you. Right, I'm gonna share my desktop. Second, I'm settling it up. Hi, I'm J.D. Patel. I work for Intel, and today I will be presenting Intel compilers' main features. The title of this webinar is Explore Parallelism using Intel compilers. And I also added kind of subtitle saying going for low-hanging fruits. And what I mean by that is I will be talking about how easy it is to use some of the key compiler features without much effort, and some things that you can achieve in a matter of minutes and perhaps under a day or so. I'm going to explain you there are lots of knobs in our compilers to attain more and more performance, but I'm just going to keep it simple. Okay. So today is going to be, I'm going to first give you an overview of the Intel Parallel Studio, the complete suite, and the composer component within it, and how it's kind of one software architecture that you will use today for optimizing your applications, and then you can scale with the same thing. You can scale forward for tomorrow. So meaning from multi-core today to many-core tomorrow without changing your strategy for optimization. And whatever the effort you put in today, the investment will be kind of preserved moving forward. I will then explain I will take a deep dive on Intel compilers, main features, but before that I'll explain you the rationale behind using the Intel compilers, why bother with Intel compilers kind of thing. As part of the main compiler features, I'll be talking about auto-vectorization, inter-procedural optimization, profile guide optimization, and high-level optimization. I'll also touch on parallel programming models, primarily on Intel Cilk Plus. That's our latest addition to our parallel programming models, and pretty useful and easy to use kind of parallelism model. And I'll close by just reviewing the quick steps for tuning using Intel compilers. Okay, so you will be getting the slides and the recording, so you have this legal disclaimer and optimization notice as well, part of the deck. Okay, so all tools for optimizations are now conveniently bundled into something called Intel Parallel Studio XE version. And it's, as you can see, it got a best HPC software product technology award, and it's pretty powerful set of tools for boosting performance, scale forward, and, obtain your investment. There are four major components of the Intel Parallel Studio. The first one is Parallel Advisor, which is basically a threading design assistant. It tells you, or it guides you in finding spots to introduce parallelism in your code. Okay. The major component, which I'll be focusing today, is Intel Composer XC. It's basically C, C++, and Fortran compilers built together with the performance libraries. We have two performance libraries, Intel IPP, Integrated Performance Primitive Library, and also Intel MKL, Math Kernel Library. Also have, like I mentioned, parallel programming models like TBB, Threading Building Blocks, and Cilk Plus as part of Intel Composer XC component. So Composer XC is basically to introduce parallelism in your code. Okay. The third component is, now that you have introduced, designed and introduced parallelism in your code, how do you verify that the threading that you introduced is correct, or there are no memory errors? So Inspector XC is useful in finding memory and threading analysis, in your code. And the last component, which is also very important component for queue purposes, for finding hotspots in your code, is the vTune amplifier XC. Okay, this is a guesswork in where the hotspots may be in your code, and if time permits, I'll show you how easy it is to use and how obvious it makes where the hotspots are and how to go about it for the optimization point of view. Okay, so as I mentioned, I'll be focusing on the compilers, which are part of the Composer XC, which is used for introducing data and task level parallelism in your code. So this overview of the Intel compilers main features that I'll be I'll be going over today in today's presentation, and I've already mentioned some of the highlights. So I'm going to keep over to the next slide, which addresses the value proposition of Intel compilers. Why use them? So the goal is achieving better performance. Okay, simple as that. Now the performance can be gained in variety of ways, and a couple of obvious ones are to scale up within the box, and when you're doing that, you scale out. While for scaling up, you can use Intel compilers and Intel performance libraries, and you exploit both level of parallelism, and I'll explain that in more detail in the rest of the presentation. For vector level parallelism and thread level parallelism, for scaling up within the box. We also have Intel Cluster Toolkit for scaling out. I'm not going to talk about it as part of this presentation, but just so that you are aware of it. Intel compilers supports all the latest features in the hardware, in the chips that come out. So your old libraries and code will run as is without much problem. However, they won't be able to extract the best possible performance, and need to use these latest compiler releases and latest features introduced in the compilers to unlock the performance of the new platform that you may have purchased. I'll explain that in full details. Last, and again, I'm not going to talk much about these Intel performance libraries as part of this presentation, because I want to focus on compilers itself. We have Math Kernel Library, which addresses various types of function domains, and I have a pointer at the end of the presentation, and you can look at the documentation and see if it's useful to you. Similarly, Intel Performance Primitive Library, IPP, that also addresses different domains such as compression, video, audio, processing, encryption, and so on. So if you use these performance libraries, that will help you also extract the vector and thread level parallelism as part of your code. So all bundled up together with compiler in the suite that I mentioned. Now, compiler is very easy to use. It plugs into the IDE, Visual Studio on Windows and Eclipse on Linux, Xcode on Mac OS. For quick and simple gains, ROI kind of experiments, the source level changes, and I will explain to you all those tricks that you can try out using Intel compilers. that is also very important in addressing why we use Intel compiler is you want to let Intel compilers do the heavy lifting for you, and you want to avoid writing processor-specific code in your source. You don't want to see if it is Core i7, do this. If it is SSD capable, then do that, because that's very difficult to understand the code, and also most importantly, difficult to maintain that kind of code for long term. So over the time to market and the total cost of ownership, you want to let the Intel compiler do the heavy lifting for you. And the last bullet on this slide is also extremely important. It is both source and binary compatible. And what I mean by that is you can mix and match components, compile different compilers. So you don't have to build everything in your project that may be, let's say, 100,000 files or so, or tens of thousands of files using just Intel compiler. You can mix components that are built with GNU compiler on Linux or Microsoft compiler on Windows, and it is fully binary and source compatible. Even within a given DLL, you don't have to build all the files. Let's say it has 1,000 files. You can find out where the hotspots are, where you are spending most of the time, and just compile those files using Intel compiler. So it's very easy to identify where you are spending most of the time using VTune amplifier, as I mentioned earlier. Okay, so just want to take a quick review of types of parallelism available in Intel processors and platforms. Okay, so the first two bullets, instruction-level parallelism and vector-level parallelism, they apply to each and every core in your box. So if you have, let's say, 8-core or 16-core box or more, those core has these first two bullets capability. And it's very important to remember, because as we add more and more cores, it's good that you can do more and more things in parallel on each core, but within each core also there is a parallelism opportunity. Okay. And the first bullet is instruction-level parallelism. So that's a microarchitecture. It's a hardware microarchitecture techniques, classical, that we learn in college. Pipeline execution, out-of-order execution, branch prediction, superscalar, and so on. It's not an exhaustive list here, as you can see. You don't have to program it or change any code to extract this performance. Compiler can help you. Intel compiler can help you to get advantage of this parallelism. The second is going to actually my focus in the talk, rest of the talk today, is vector-level parallelism. So each core is capable of something called SIMD, single instruction, multiple data, meaning with single instruction, it can operate on multiple set of data depending on the data types. I'll explain that. I have a graphical presentation of this phenomena, and I'll explain that in later. But the point I'm here trying to make is Intel compiler makes it easy for you to use the SIMD instructions under the hood, so that you don't need to learn those, and it will introduce those instructions under the hood for you. Two bullets are applied to each core, and the third bullet is very obvious to everybody nowadays, thread-level parallelism, meaning as we add more and more cores, and also with the help of hyper-threading, simultaneous multiple thread allows multiple threads running in concurrently on a single box. It's pretty obvious. I'm not going to spend too much time on it, because a lot of threading mechanisms are available, and now threading abstractions are also available. Although I will touch on something called Cilk Plus that we introduced recently as a powerful tool to exploit the parallelism. The fourth is also not going to be focused as part of this talk, but just for the sake of completeness, it's a node-level parallelism, meaning once you optimize within the box and you exhaust all the cores inside the box, you go across the boxes using cluster toolkit, in a distributed fashion. Okay. So what is this vector-level parallelism, or even some people refer it as a data-level parallelism within each core? Okay. So this one is, so look at this simple loop, adding two vectors and putting the output into the third vector. In scalar mode, it will just take one element of A and one element of B and add it up as A plus B and put it into the C, as you can see on the left-hand side. And it will do this each time as it iterates through the loop. Now, using Intel compiler with a special switch for SIMD vectorization, we can add, in this, for example, 8 dimensions within a single clock. So this piece of code will be running 8 times faster. Okay, and when I say 8 here, it's a floating point data type, and this code is done for AVX, and I'll explain that why it is 256-bit wide. Okay, so how the Intel compiler can help me extract this 8 times faster, 8 times speed up in this previous example that I showed? So there are multiple ways you can exploit VLP using Intel compilers. We offer inline assembly, we offer SSE intrinsics, we have SSE vector classes, but these all I tend to think as hand tuning, meaning you have to invest a lot of time. It's very hard to learn and debug and maintain and so on. What I would recommend is to use something called auto-vectorization. The details coming up in the next few slides is the fastest and easiest way to use to exploit the vector parallelism in each core of your machine. I also explain something called array notation, which is part of our Cilk Plus for predictable performance to exploit the SIMD capability of each core. And just as a reminder, if you use those two libraries that I mentioned, performance libraries, IPP and MKL, automatically under the hood, they will exploit the SIMD capabilities. So, for example, if you have a need to generate random numbers, if you are doing a zlib or a BZIP2 kind of compression, or any encryption and so on, you just invoke those function calls from these libraries, and you do this parallelism under the hood for you, meaning you don't have to worry about it. And you do it for the processors that you are using today, and you just replace the libraries, not change your source code, next generation processors, and still magic will be done for you. So, as a reminder, what is automatic vectorization? So, the compiler has a component called auto-vectorizer, which looks at your code and it performs the analysis and see if it is possible to introduce data level or vector level parallelism using SSE or AVX instructions, depending on what you have specified as your target processors, for the most part without changing the source code. I'll explain what I mean by for the most part, or no significant changes to the source code in a couple more slides. This is much more easy to learn. In fact, there is no learning. I would explain what I mean by that. Not much learning at all. It's very easy to debug and maintain and forward-looking approach. So and you can use these for both Intel and AMD processors. You can target and you can generate the same binary that can address those types of processors. If you mix processor environments, let's say you have Core i7 and Core i7 with AVX support, and you also have, let's say, SSE 4.2 instruction-based processors, you can create a single binary that can run on AVX-capable machine, SSE 4.2 capable machine, and also an older laptop, say, using only SSE 3. So, and do that. So the third bullet talks about processor-specific optimization. So, for example, if you know that in all the machines that your binary is going to run on is SSE 4.2 capable, what you have to do is supply a switch called in Windows QX SSE 4.2 or DASX SSE 4.1 Linux, and the generated code will be optimized using SSE 4.2 level instructions under the hood for you. Okay. If you know that your clients maybe or your binary is going to be deployed in a hybrid environment where some could be AVX capable, the latest machines, some could be SSE 4.2, let's say machines purchased last year or so, and some even 3-4 years old SSE 3 capable only machines. In that case, you use this auto-dispatch feature of the compiler, and you provide this switch. So looking at the very last line on this slide is if I provide Qvec for automatic, ADX, SSE 4.2, you'll generate 3 different code paths inside the binary. One is one that can take advantage of AVX, the other one SSE 4.2, and it will also have a default SSE 2 generic code path. And runtime, when the binary is launched, it finds out which type of processor it is running, and it will go through the optimized path targeted for that particular processor. So as you can see, it's very easy to use, and here is an example. So the same example that I explained in a graphical fashion, what I mean by auto-vectorization is, I add 2 vectors A and B and put it into the C. All I have to do, as you can see, is, when I compile, I have to specify the switch called -x-ADX, and I generate also the vectorization report to find if the loop was vectorized, and I can get this remark say loop was vectorized. Now, this is obviously a trivial example. It does show the power of what compiler can do. Instead of adding 1 element at a time, you can add 8 elements at a time. And now I address what I said earlier. It is 8 and not 4 or other number is because this is targeted for AVX capable processor. AVX processors have a 256-bit wide SIMD registers, and the data type here is floating point, which is 32. So it can 8 of those 32-bit processors, 32-bit data type processing within 256-byte register. So 256 by 32, it gives us 8. So it is like that. Now here's a real-life example that I derived from one of the professor's website to calculate stocks auction price using Black-Scholes formula. And it's a pretty complex code, okay? It does square root, logarithm, in this formula. It has exponent and a whole bunch of multiplication, division. It invokes one function, invokes the other, and so on. So it's not a trivial, simple example. It does a lot of mathematics. If I compile this code using -x-AVX, as you can see in the red bottom, and generate the vectorization report, I get the loop was vectorized. And now this is a double precision. This is not floating, double precision code. So it will only do 4 code paths simultaneously, meaning the single instruction will be able to work on multiple data, but that multiple is going to be 4 times. So I just did a new laptop which AVX capability. This serial code and then AVX compiled code, it runs 4 times faster on each core. Okay, I'm not talking about the whole box. With each core, I can go 4 times faster using this automatic vectorization. Now, a few things to remember when you are doing automatic vectorization. I just left it in here. I'm not going to go through all of it for the sake of time, but just you have something to refer to when we are done with the presentation, and we have a whole bunch of documentation on site, online, with some papers and some articles on what to do, what not to do, kind of thing. So you want to focus on hot loops, meaning let's say your program has 10,000 loops. You don't need to vectorize all 10,000. If the compiler does not vectorize a loop that is not of significance, it's okay. You can let go. And you can use vTune amplifier to find out what are your hot loops, and then make they are getting vectorized by generating the vectorization report. There are pragmas, and actually I have to the next slide. Sometimes some loops don't get vectorized, and the vectorization report, when you generate using -Qvec-report on Windows, -vec-report on Linux, you get a loop not vectorized because of some of these reasons, and these are only some of the examples, meaning the inner loop gets vectorized. Sometimes the loop doesn't get vectorized if there is a low trip count, meaning the compiler does the cost-benefit analysis and thinks that it's not worth vectorizing the loop. Now, if you are sure, you can override this cost-benefit analysis by using pragma vector always. Okay, changing your code, you're just adding a pragma to guide the compiler. Hey, I know what's going on. You can also, sometimes it does vectorize if the arrays are going to be overlapping. If the input and output vectors could be overlapping, the compiler would not vectorize. In that case, if you know that they never overlap, we have pragma called pragma IVDEP to address that situation. So again, documentation is online, so you can take a look later on. So guidelines for writing vectorizable code. So the loop should be countable, okay, and the loop should not be changing the loop count on the fly from within the body. Any single entry, single exit kind of loop. For loop meaning, shouldn't be breaks and go to jump kind of statement within the loop. So simple lines, if you follow, it will help you vectorize some of the important hot loops. And again, to remind you, you want to keep all this thing in mind only for the hot loops and not for all the loops. Okay, so I'm not making a recommendation to go and vectorize all the loops, which is quite unnecessary. Okay, for example, let me show you very quickly. Very easy. So here is my code that I analyzed using an amplifier. All you have to do is just right-click and say vtune amplifier, perform a hotspot analysis. It generates this. After running the program, it generates this hotspots list for me. And I can just simply double-click on a function. Okay, I'm spending so much time. And here's the loop where I'm spending 14 seconds on this line and 13 seconds on this line. Now, this I deliberately used the pragma no vector, meaning I wanted to force serialization of this loop. So here I know that this loop is important. So in my next all I did is pragma simd. That's another way of forcing or enforcing automatic vectorization for Intel compiler. So as you can see, I did not have to change the code. I did not change the logic of my code. I just added a pragma. So it's fairly straightforward to use. And these are some of the math functions that can get vectorized by compiler under the hood. So if you recall in my program, I'm using exponent, logarithm, all those functions, but under the hood, compiler will use something called svml underscore exp or svml underscore logarithm. So all these math functions get vectorized, and they can operate concurrently on multiple input data elements depending on the data types that you are dealing with. Is there a question on automatic vectorization so far?
We do question, if I use the IPP library, do we also need to do auto-vectorization?
It's kind of yes and no, because IPP library, IPP function calls, they will be vectorized. So for that sake, you need to do automatic vectorization. However, for a piece of code which is not invoking IPP, meaning let's say you have 100 lines of code and 10 of those lines are invoking IPP functions. So for that portion you are covered, but for the rest of the 9 lines, you may want to use automatic vectorization to take advantage of SIMD capability beyond the IPP uses. And same thing applies for MKL as well. If there are no other questions, I'll jump on to these next 2 major features. The first one is the IPO, inter-procedural optimization. So this is the optimization at the build time by performing static analysis of your code, okay? The compiler looks at the code, and it has the capability of analyzing the code either file by file or across the file. And I'll explain on the next slide what I mean by file by file or across the file. But The benefits of these IPO analysis is it can optimize large number of frequently used small and medium functions. Okay, the keyword here is small and medium functions. They get inline. Okay, so it's beneficial, especially if they are called in the loop. Okay, so for example, I switch back again to my in my code. So when in this function, when I invoke this function, let me go to the definition. It's a very small size function, as you can see. The body is not that large. Okay. Now I not inline this function. The compiler does inlining for me, and that's the point here I'm trying to make. It does automatically. All you have to provide is -IPO switch when you are building, and that's it. It will do the analysis. It will do the cost-benefit analysis. Cost-benefit because you don't want to see compiler inlining very large function, right? Because it defeats the purpose. Now, function gets inline. You can see the advantage. It can boost it dramatically the performance of your binary because it eliminates the need for argument setup. To call, meaning branch to that location and return overhead. Argument setup and so on. Yeah, it also enables the opportunity for vectorization. So IPO helps automatic vectorization, which was the case in my code. If again, I apologize for flipping back, but if I go back to this function body was inline, and therefore it got vectorized. This loop was able to vectorize. So it really helps when you put together these compiler main features together. It is also better to use IPO with PGO, and what is the PGO is coming up next feature. I'm going to discuss profile-guided optimization to guide even better function inlining. Now, I use IPO. It may increase your build time and binary size, obviously, because the compiler has to do more work, meaning more analysis during the build. So here's a view of what it does is it's a two-step process, right? In the compilation phase, it creates something called files, information intermediate representation files, and then during the link phase, it performs the IPO on all the files containing the IR information. Now, you can choose to do only a single file IPO if you provide -IP switch, or you can do multi-file IPO using -IPO. Now, I also have a tip here. If you have like tens of thousands of files, you don't want to use -IPO because sometimes it has a tendency of running out of memory and so on, because the generated data will be so large that may not be able to handle. So you may have to carve out pieces of your project, or just use single file IPO. Try that out, but it's really worth trying that. Feature that goes along with it is profile-guided optimization. So optimization done by the compiler with a runtime feedback. So in your code, if you have something like x greater than y, do these, or else do that. Now, how often x is greater than y, right? I mean, that info is not available at the build time, so you have to have runtime feedback, and that's the key here. Or you have a loop here in the picture. So what is the value of count? The compiler may not auto-vectorize. You provide the -XAVX switch, for example. It doesn't see the count is large enough. Okay. One option is to provide the pragma loop count and say, hey, no, I know loop count is always going to be less than north of 1,000, more than 1,000, and go ahead and vectorize the loop. The other way is you perform this PGO analysis, and automatically finds out what the count is. So a three-step process. In the first step, it generates the instrumented binary using profgen switch. And once this instrument binary is generated, you take this and run it through your typical workload. Okay, so that's second phase. So your instrumented execution phase, you run it with the typical workloads. And when you gather the data of multiple workloads, you feed it back and go to the third step, which is feedback compilation phase using profuse. And all the dynamic information that was generated in the previous step will be looked at by the compiler, and now it can generate the most optimized binary that you can deploy. So benefits of the page view are quite obvious. It improved branch prediction for one, so it's very good for your branchy apps. It generates very good better data and code layout, meaning it can do, for example, frequently access code placed functions placed adjacent to each other, which improves your instruction cache usage, and batching and decoding and so on. If you have switch statement, it can optimize that too. Like if you have, let's say, a large switch statement with 25 cases, and most of the time you are hitting case number 10 and 15, rather than doing if-else all the time for all the cases at runtime, it will bubble up those 10 and 15 number case statements up. You changing the code under the hood in the binary. So your optimized binary will be much faster and much better. It will help you do better function inlining, because now you know what are your hot functions and not the cold ones, so the compiler has much more information. So there are benefits, and this is not the exhaustive list. You please refer to the documentation for that. This is just a graphical view of what happens. We talked about it of the three different phases. So I'm going to skip slide. Last feature for the low-hanging fruits particularly is to use dash parallel switch. Dash parallel switch comes in quite handy if you don't have much time to analyze your source code and introduce parallelism on your own. So when you provide this dash parallel switch, the serial portion of your code automatically gets translated into multi-threaded code whenever compilers see that as a possibility. So this obviously frees developers from having to determine, is the good work sharing portion in my serial code. It doesn't have to do data flow analysis to find out, is it okay to introduce parallelism over here, because compiler does all the job for him. Okay. Obviously, it partitions the data for the threaded code, and then it distributes and gathers the results and so on under the hood. And it follows the same features as in the runtime follows the same features as in OpenMP, so that makes life even easier and much more efficient. All you have to do is just use the dash parallel switch, and you're done. Okay. And the last bullet says if you know it is safe to parallelize a given loop, you can there is a pragma parallel if you like to use that. So here's an example where I can combine automatic parallelization and automatic vectorization. The loop, when I use dash parallel and dash x SSE3, for example, and it would be dash x AVX for the current processor. This is a bit dated slide, as I can see. The loop will get vectorized, and you can see in the vectorization report that I generated, the second last line on the slide says loop was vectorized. So that inner loop that got vectorized. And the inner loop was vectorized, meaning it can do can operate on multiple input to generate output on a single core. It can then parallelize, meaning the outer loop gets auto-parallelized, and it can spread across your multiple core. So this thing is done automatically using just Intel compiler with proper switches for tuning. I encourage to try out this high-level optimization that gets kicked in. You use -03. I can know that a lot of customers just leave optimization just label at -02. I have -03 because at -03 Intel compiler can do much more aggressive data dependency analysis and other stuff. It can do a lot of loop transformations, and here is a list like loop distribution, loop fusion, interchange. It can interchange inner and outer loop. It can fuse loops. It can distribute and unroll and so on. So it's always worth trying this option out and see if it helps. Then you keep it. Otherwise, you can roll back to -02. All these features are so easy to try out. Just a stroke of a compiler switch, and you will see the results.
We do have a couple questions that just came in.
Sure.
One is how well does the auto-parallelization work on the code that has all dynamically allocated with the sizes determined at runtime?
Good question. The answer is it depends on, I'll have to take a look at the code. It depends on code because there are a lot of other complexity also that needs to be analyzed by the compiler. But the answer, it should work. But if you have a spatial test case that you want, you tried and you think it should be parallelized and it is not, I'll be more than happy to take a look at that, and I can work with our engineers to find out. But it should work.
Okay. And the other one that popped in, and just so you know, we've got about 15 minutes left, is we use MSVC10. How easy is it to integrate ICPC? And along with that, is the ICPC transparent with MSVC process? Okay,
so the answer is yes. And now ICPC and ICC are for Linux. I'm deliberately mixing those. In Windows, we call it ICL, but the example is right in front of you. All you have to do is, in fact, it's so nicely integrated here. All I have to do is, if I want to use Intel compiler, using Intel compiler, so I can, if I want to switch back, all I have to do is just click on this, and it will switch back to the Visual Studio C++ compiler, and vice versa. When it is in Visual Studio compiler usage, if I'm back here, right-click on my project and come back here, I can switch it back to Intel compiler. So very easy. And not only on a project base, you can do the same thing also on a file-based. You can do guided parallelism and so on. So there's a lot of flexibility. You can go to properties and you can choose the C++ compiler and so on. So it's fairly straightforward. I hope I think I demonstrated the use case, but it's not ICPC in Windows. It's more for Linux. Okay. Well, so the word on floating point again. I have some slides that just for your reference that you can refer later on, and I have some pointers that you can go on online and check it out yourself. Typically, customers want to achieve all three conflicting goals simultaneously. That is, they want to see accurate result. They want to be able to reproduce on a different machine the same answer, different platform, different compilers, different run, and they also want to have performance, best performance as possible. So this conflicting it's a trade-off, right? It's a conflicting objective. But you can come close to achieving it by using this thing that I highlighted. You can use floating point model, precise and source. I'm not going to go through the details, but you can refer for details. Please refer to this beautiful white paper written by a couple of my colleagues, and that will explain you how you can go about achieving these goals. And it's basically the compiler offers you knobs where you can control what is your priority among those three objectives. Okay. We're going to wrap up talking about, again, a few more slides for parallel programming models. So the compiler does offer you flexibility when it comes to introducing parallel programming in your code and automatic vectorization. So we have something called Cilk Plus. It's basically vec extensions for simple parallelism, and I'll show you in a slide. We also have something for multiple years. We had threading building blocks library, which is also already open sourced. So you can go to threadingbuildingblocks.org. Even Cilk Plus, we have open standards already, and it is being worked on to get into a GNU compiler for Linux. We have domain-specific libraries I already mentioned, IPP and MKL in the middle. We obviously support all these established standards, meaning you can use it with MPI, OpenMP, and so on. And we have some research development projects. So with that, I want to just quickly talk about Cilk Plus. But I have one more slide I just realized. Here is my recommendation. Use Cilk Plus notation for vector parallelism in addition to automatic vectorization that I already discussed. This is to use, and I have a couple of slides on that. You can use Cilk Plus for task-level parallelism, and I'll show you, which is very simple and very easy to use, just like OpenMP or TBB, perhaps even simpler at times. And also use TBB for task level parallelism. Okay, Cilk Plus. Actually, I'm going to skip this slide. Cilk Plus is primarily made up of 5 main features. It got few keywords. It got array keywords for expressing task level parallelism, and I'll show you that. And we got a notation for vector level parallelism. We got reducer to reduce the data to resolve the data races for shared variables. And we got elemental functions for expressing vector level parallelism. We have SIMD pragma. So let me show you. So these are the 3 keywords. Very simple. If you want to spawn a thread, you just call Cilk spawn. If you want to sync and wait and synchronize all the spawn threads, you could just call Cilk sync. And if you have a for loop that you want to parallelize, you just call Cilk for. So here is a simple example. If I want to, this is a Fibonacci calculation, and if I want to parallelize these 2, I can just, all I have to do is Cilk spawn. I just add a keyword in front of fib -1, and I'm done. You know, it will run in parallelism depending on the opportunity available. Then I synchronize by Cilk sync, because you do want to get accurate numbers on X and Y, and just return. So it's fairly straightforward to use. Your loop, all you have to do is just Cilk for instead of for, and it's you're done. I mean, it has to be countable and loop. There are some constraints, obviously, but it's fairly straightforward to use. So this is a summing example. Converted the serial code by using Cilk for, but as you can see, there will be a data race because multiple threads are now trying to update this result. So one option is to add log, which is not that good from performance point of view. So Cilk Plus has something called a reducer. So if you define result as a op-ed reducer in this particular case, what will happen is the result will be accumulated by each thread on different cores independently, and then it will be merged under the hood for you. So it's much more quicker, much more efficient that way. And, so array notation, that's for vector level parallelism. This works with automatic vectorization that I already described. It works on array slices, so you can here it means this is the low bound. It can have lower bound, then there is a length, and then there is a stride. So it's pretty powerful actually, and you need to use all the features of that. You can address all the elements of the vector A just like that, and B, if you want, start at 2 and go up to 6 elements, you can do 2 colon 6 and so on. So where you use, and I have a code example, it will also let you work with your regular C++ operators, meaning you can do A colon times B colon in this particular example in the second bullet, and it will be fine. In the last bullet, you can also you can have a scalar operand automatically expanded. So a bunch of examples over here. I'm not going to go through them for the sake of time, but if you have any questions, of course, shoot me an email later on or ask me a question now. No problem. Let me actually show you a simple example of array notation. So I have a Qvec function that we created using array notation. So meaning for each element of Y, I want to assign the value A times each element of X. So for when so it's basically, as you can see, it's converted for into this one single statement, which is quite real, and now it is vectorized as well. And then I can invoke these functions even. So this for a vector array notation gives you data level vectorization for each core, and then you can use Cilk for to parallelize across multiple cores, okay, for multi-threading purposes. I even have, so the other capability of Cilk Plus is elemental function, where you can define your scalar function just like that. This is the original function. All you have to do is just add a decal spec vector in front to have that function vectorized, and then you can invoke in a loop. Okay. Here is my example modified. Okay, this is the same source code of option pricing that I showed you earlier. The only thing I did is changed in green. I just added the decal spec vector for these 2 functions, and I invoked that using array notation, and it starts working 4 times faster on each core. because this is, as I mentioned, this was a double precision calculation. So 256 by 64 is that 4 times speed up.
There's a question that just came in about that, JD.
Sure, go ahead.
Okay. Will array notation in Fortran automatically vectorize?
Okay. I'm not a Fortran guy, unfortunately, but if you capture that as a question, because I don't want to, I'm tempted to say yes, but I don't want to say affirmatively. I would rather have it answered by my Fortran expert colleague. Like Fortran, this feature is like Fortran-ish. I'm sorry, I don't want to say yes for Fortran. Okay, well, these are some of the new features that we added. Well, as you can see, we always keep adding features in the compiler, and you do want to use the latest and greatest compiler all the time because we keep on adding switch, we keep on making further enhancement in our compiler. So, for example, if you have like 3-year-old compiler, it would not even work and recognize on ADX instructions, so it won't be capable of that. So you have to upgrade like any software. So here's a quick summary of what I talked so far to how you can go for low-hanging fruits without doing open heart surgery on your source code. So first, you always want to make sure that your code runs correctly at as a step 0 using O-debug or -O0 in Linux. Then you can start optimizing using -O2, using general optimization -O2, or you can even and also want to move up to -O3. When you use -O3 along with other optimization switches, number 2 is automatic vectorization. It will be quite useful. Automatic vectorization, we already talked. You can use either specific targeted processor, one single type of processor, or you can do an auto-dispatch for multiple types of targeted processors. When you do these, I prefer to use vTune to identify your performance hotspots, which is very straightforward. I already showed you, and I can answer questions on vTune if you have to find out hotspots. And then you combine that with you look at your hot loops and say, hey, this is my hot loop, so I'm spending 10% or 20% of my runtime, and it's not getting vectorization report. It's not getting vectorized. If I look at the vectorization report, then you go and address the issue, okay? Meaning you want to go for optimizing all the loops. Number 4, try out the -IPO for inter-procedural optimization. That will help you inline your small to medium-sized functions. Very useful if you have loopy code particularly. Also try profile-guided optimization, that 3-step process that I explained, and this will be very good for your branchy type of applications. It's excellent to combine IPO and PGO to help optimizations for particularly automatic vectorization. Once you do that, you can also exploit further multi-core parallel simultaneous multi-threading using Cilk Plus, Cilk threads that I mentioned. You can use TBB, OpenMP, or your favorite, any favorite threading abstractions to exploit multiple cores. And of course, you can use vTune amplifier to find out what your threading efficiency, what is your threading correctness, and that's also very easy to use. I showed you here, for example. I can see that how many threads, Cilk worker threads, are running under the hood. Here I parallelize using Cilk 4, meaning all I had to do is just, instead of this for loop, I converted it as Cilk 4. I touch anything else. I just added Cilk 4, and all of a sudden I can see that it's running in parallel for me. Okay. Here, deliberately, you can see that this portion, I can obviously see this portion is only single-threaded, and I know that because I deliberately created a serial loop at the front, running on one core, so that's why. And then I started running on all my 4 processors. So easy to use this kind of optimization tools, which are part of Intel Parallel Studio. With that, I will show you. The deck also contains the link to Composer XE that I just described, and also the whole Parallel Studio XE. And if you have any questions, that's my contact information. So with that, I'll turn it back to Sarah for remaining questions and summary.
There are a couple other questions. Does auto dispatch have any negative impact on older processors? And then along with everything else, does everything that you've discussed apply to the Mac version of the compilers?
Yes to the later question. For the auto dispatch, there is no negative. There is no negative to older processor. It's just that you want to make sure that it won't go below SSE2, of course, but if it's not going to penalize if that's what you are wondering. Now, it may not run if you did not do a proper auto dispatching, meaning if you just left it as a AVX, meaning automatic dispatch for AVX only. So it will do it for AVX and SSE2. It's not going to do for SSE 4.2 because it did not request. So if you run it on a Nehalem processor, in that case, it's not going to take advantage of SSE 4.2 instructions because it's not going to be able to run at AVX level, right? And so it will fall back to the SSE 2 level. So that is kind of a penalty, but that penalty occurred because I forgot to add SSE 4.2. So in that case, I should have done, like I mentioned, let me find that slide, sorry. Okay, finally. So you can see the last on this slide, I should have done AX, AVX, comma, SSE 4.2. So in this case, it will create now 3 code paths, AVX, SSE 4.2, and SSE 2. That way, I'm not getting penalized on my 2-year-old SSE 4.2 processor-based machine. So as long as you don't, if you do proper, provide the proper switches to the compiler, there is no penalty as such.
Okay, JD, and I think that that's all the questions that I see for now, but if anybody does have any more questions, go ahead and those email addresses are up there if you want to send them.
And I want to thank G also for hosting this today, and to everybody on the line for attending. If you need to contact us by email, please do it, info@techextend.com. Or on the web at www.techextend.com/intel, or on telephone at 800-221-7710. So again, thank you everybody for attending. Thank you, JD, and have a great afternoon.
Thank you for your time.